In this video, we're going to look at exponential functions and logarithmic functions. First, exponential functions. So an exponential function is a function where the variable is actually in the exponent. So they take the form of a constant I'm going to call c times another constant b to the x. So I'm using b for base. And the x is the independent variable, which is the exponent on the b, and then sometimes you have a coefficient out front, which I'm going to call c. So we're going to start with two simple examples, just 2 to the x and a half to the x, which we're going to graph by plotting points. So plugging in, for example, 2 to the minus 2, that means 1 over 2 squared, or 1/4. We'll plot all these in just a moment. 2 to the 0, anything to the 0 is 1. We have 2 to the first, 2 squared, I'm just going to jump 2, it is 4, and 2 cubed is 8. Okay, so plotting those points down here, we have -2, a fourth is right about there, -1, 1/2, 0, 1, 1, 2, 2, 4, and then 3/8 a little off the graph. Now what would happen if we put in -3 or -4 or so on is we would just get smaller and smaller fractions which are closer and closer to 0. So this exponential function hugs the x-axis right there. Okay, that's to the best of my drawing ability, but it hugs the x-axis right here. In fact, the x-axis is actually a horizontal asymptote. So we can mark that. That's the line y equals 0 is a horizontal asymptote for that graph. Okay, and that's called an increasing exponential function because as x increases, the y's also increase. Next, let's graph g of x equals 1/2 to the power of x. Okay, let's start down here. So if we do 1/2 squared, a half times a half is a fourth. So when x is 2, y is a fourth. Then a half to the first is, of course, just 1/2. So 1, 1/2. A half to the 0 is 1. They both go through that point. Okay, a half to the -1 means 1 over a half to the positive 1, and 1 over 1/2 is 2. So it goes through -1, 2. Or a half to the -2 means 1 over 1/2 all squared, which is 1 over a fourth, which is 4. And you get the pattern. So this one's going to simplify out to be 8, which again is off my graph here. Now this is called a decreasing exponential function. It's the mirror image of 2 to the x across the y-axis. Okay, and another way to look at this is that 1/2 to the x could be written as 2 to the negative x. And so if you look at it like this and think of function transformations, you may remember that when you put a negative right in front of the x, that flips this graph over the y-axis. So that's exactly what we have. So you could write that as 2 to the negative x or 1/2 to the positive x. If we just stick with positive exponents and we leave it as a fraction, here are some patterns then. So anything of the form f of x equals b to the x, where b, the base, is greater than 1, would be an increasing exponential function. Or if the base is between 0 and 1, you would have a decreasing exponential function. Now if the base b equaled 1, you'd have 1 to the x, which would, because 1 to any power is 1, essentially, you would just get a horizontal line. So that's not even really an exponential function. And we're not going to deal with negative bases because that's for a more advanced branch of math. It doesn't make sense in our context. Okay, so some properties of this. You can plug in any x into an exponent. There's no problems with that. So the domain is from -infinity to infinity. The range, well, no matter what x you plug in, you're never going to get a negative value. B to any number is always positive, always greater than 0, in fact. So the range is from 0 to infinity. They never touch the x-axis, so there's no x-intercept, but the y-intercept is the same no matter what, as long as you have a function of the form b to the x without that coefficient c, because b to the 0 is always 1. the x-axis is always going to act as a horizontal asymptote. And if b is greater than 1, you're in this case, which means f of x or y is an increasing function. Or if b, the base is between 0 and 1, a fraction, then f of x is decreasing like this. Okay, they all go through the points 0, 1. The other point that I usually graph is when x is 1. If x is 1, then it's going to go through 1, b. And both of these do pass the horizontal line test. You could draw a horizontal line anywhere through it. You're only ever going to touch 1 point at a time, no matter where you draw that line. So they are 1 to 1, which means they have an inverse. They have an inverse there. Okay. Here are some various graphs with different bases. So you can see a base 2 here in red is not quite as steep. The base 3 is in green. It's just a little bit steeper, and the bigger the base, the steeper that function gets, and the more quickly it hugs the x-axis out here on the left. All right, we're going to begin a graph by using transformations. So what we're going to do is start with a parent function for this graph, and then graph it using transformations and find its domain, range, and asymptotes. Okay, so the parent function for f of x equals 2 minus 4 to the negative x would be y equals 4 to the x. Okay, so 4 to the x, I'm going to plot 2 points, 0, 1, and then when x is 1, the y value would be 4. And we know it's got this horizontal asymptote there, and then it just comes up very steeply, very quickly. It doesn't quite go vertical, although it may look like it. Okay, now the order in which we apply the transformations is the same order we would apply these things if we were to plug in a number for x. So if you plug in a number, the first thing you do right there is make it negative. So the first transformation is going to be to graph that. Now when you put a negative right in front of the x, that flips it over the y-axis. So it would look roughly like that. Okay. Then the next thing we would do is apply this negative in front of the 4. Well, after we do 4 to the negative x, then we'd multiply it by a negative 1, and then we would add 2. So next I'm going to graph y equals the negative of 4 to the negative x. Now when we put a negative out in the front of the parent function, you may recall that that flips the graph over the x-axis. So now our graph looks like this. And then the last transformation is this 2. So we would add 2 to that value right there. And we'll do the final graph in red. So 2 minus 4 to the negative x shifts all these points up too. And the easiest way to graph that is to also shift up the asymptote by 2. So the vertical asymptote is currently at y equals 0. If I shift it up 2, it's going to become at y equals 2 right there, which answers that question. Where are the asymptotes? And then we'll shift up these 2 points here. So this green point goes here, this green point goes here, and that's really enough for a pretty decent graph. So this would be the graph of our function by using transformations. Okay, its domain is the same. You can plug in any x, and there's no reason why not, so all real numbers. And its range you can get from looking at the graph now. All of these y's are covered by this graph all the way up to y equals 2. So the range would be from negative infinity to 2, not including 2. Okay, next we're going to look at a more general type of exponential function which may have a constant c out front. So first what we're going to do is find an exponential model that has this graph. Okay, and we know an exponential model is of the form y equals c times b to the x. So in order to find that model, there's really 2 unknowns. We need to find both c and b. And we're going to do that by plugging in any of these points, any two of these points actually. So I'm going to go with some easy points to make this simple. 0, 1 is an easy one to plug in. So if we plug in 0, 1 into that function right there, when x is 0, y is -1, so we have -1 equals c times b to the 0, and b to the 0 is equal to 1, so that tells us that c is -1. Okay, so that's helpful. So now we have the model y equals the negative of b to the x, and we could plug in any of these other points in order to solve for b. So I'm going to plug in 1, -2. So if -2 equals the negative of 1, or negative of b to the first. B to the first is just b. Divide both sides by -1 or multiply, and we get 2 equals b. And that's all we need in order to have our model. So then our model is y equals c, negative, b, which is 2 to the x. Okay, and to be clear, the negative is separate from the 2 to the x. Okay, it's the negative of 2 to the x, which is not the same as -2 all to the power of x. We are not including that negative. That would actually have a negative base, which would be something totally different, which we're not dealing with. So there is our model, or our function that would have this graph. And you could have plugged in these other points also to solve for b, and you would have gotten the same thing. Okay, looking at exponential functions, I want to look at what happens over equal increments of time, or over equal increases in x. So when you have an exponential function, what happens, like for example with 2 to the x, what happens is your y values multiply by the same amount with each constant increase in x. So every time x goes up by 1, if your function is 2 to the x, your y value doubles. So to go from 2 to 4, we doubled. From 4 to 8, we doubled. So that's what an exponential growth function does, is it increases based on a constant multiplicative rate of change over equal amounts of time, as opposed to a linear function where you simply add equal amounts to the function over equal amounts of time. So all of these y values are just increasing by 2 with each step. So that is a linear change right there. Okay. Exponential decay occurs when you have a decrease based on a constant multiplicative rate. So basically maybe you're dividing by 2 each time, or dividing by 3 each time or something. It's just you're decreasing, but at a multiplicative rate. Okay, so first example, a population of 30 dogs increases by 20 every year. Determine the function p of t that models the population after t years. Okay, so if you're increasing your population by this constant amount each time, by 20 dogs every year, that's actually a linear function. Okay, so we would start with 30 dogs, and then with each year after that it increases by 20. So we could say 30 plus 20x. When x is 0, you have 30 dogs. When x is 1, you've got 50. Then the second year, when x is 2, you've got 70 dogs. That is not an exponential function. That's a linear function. But this one, a population of 20 rabbits quadruples in size every 2 years. Well, that means that it's multiplying by a number, a constant number, with every equal increment in time. So this one actually is an exponential function. So we're going to determine the function p of t that models the population after t years. So p of t is an exponential function, so it is of the form c times b. I'll just change the x to the t there. C times b to the t. All right, quadruples in size every 2 years, and we start with 20. So let's just start with the fact that we start with 20 rabbits. So that tells us that when t is 0, when we start our counter, we have 20 rabbits. So p of 0 is 20. So we can say 20 equals c times b to the 0. And this is nice because b to the 0, again, is 1. So we get that 20 is equal to c. Okay, and with every exponential function, this is going to be the case. The constant out front, that c, is always going to be your initial amount. So you actually don't even have to write this out. You can just jump straight to here if you know that the starting amount is equal to that constant. Okay, now we can plug in another point to solve for b. So it quadruples in size every 2 years. All right, so after 2 years, we can say p of 2 it would be 80 if it quadruples in size. So 80 would equal 20 times b squared. And we can solve this for b. So 80 divided by 20 is 4. And solving for b, take the square root of both sides. Now normally b could be positive or negative 2, but since we are not considering negative bases, we're just going to go with b is positive 2. And now we have our model. P of t equals c, which is 20 times 2 to the t. So that is our exponential model for this example. Okay, and here's another one. Determine whether the table could represent a function that is linear, exponential, or neither. And if it appears to be exponential, we're going to find a model that passes through those points. Now I've actually got a little typo here. That should say 80 as my first point. Let's go ahead and correct that there. Okay. So let's see. One way to see is if it's decreasing by the constant multiplicative amount each time. So, for example, if we were dividing by 2 each time with each equal increment in x, it would be exponential. Well, it's kind of hard to tell with these numbers. So let me open up a calculator here. Okay, so let's see what we are dividing by each time. So you can do it either way. You can do 80 divided by 61 or 61 divided by 80. So if I do 61 divided by 80, I'm getting 0.7625. We'll just remember that for a second. Now let's see if we are dividing by the same amount with the next increment. So I'm going to do 42.9 divided by 61. Okay, it's not exactly the same. Kind of close, but not exactly. And then 25.61, let's just, 25.61 divided by 42.9. Can't seem to do it. There we go. Okay, we get a completely different number, 0.5969. So this one is definitely not exponential, and I should have actually looked to see if it's linear first. So if we do 80 minus 61, it looks like we went down by 19. Clearly it's not exactly the same because we jumped from a whole number to a decimal. But if I do 61 minus 42.9, you can see, okay, it decreased by 19 in the first increment in x, and it decreased by 18.1 in the second. It's going to be a little bit different on the third. So it's not exponential or linear. Now I do want to show you though how to find the exponential model, how you would work this if you thought maybe it was exponential, because that's a skill you need to have for when you're not given when x is 0. So in the two examples we did already where we found the function, we actually were able to plug in when t or x was 0, which made it really easy. But in this one we can't do that. So let's see, we need our basic function, which is of the form y equals c times b to the x. So what I'm going to do is I'm going to find the model that goes through these first 2 points, and then we'll show that it doesn't also go through these 2 points to really show that it's not exponential. But I want to show you how to find the model that goes through 2 points, not when x is 0. Okay, so we're going to start by plugging in 1, 80. So when x is 1, y is 80. And I really can't solve for b or c explicitly at this point. So I'm going to have to go ahead and plug in the other point. When x is 2, y is 61. So we get 61 equals c times b squared. Okay, so what we have here is actually a system of equations. right? I've got, it's a comma, I've got these two equations both involving a c and a b. So it's a system of equations which we can solve for c and b. Okay, so I'm going to solve this first equation for b. So we get 80 divided by c is equal to b. And I'm going to plug that in for that b right there. We'll do it over here though. So I have 61 equals c times 80 over c all squared. Now we can solve this equation for c. So I have c divided by c squared here. So one of those c's cancels, so I get 61 equals 80 over c. And I want to solve this for c, so 61c equals 80. So c is 80 over 61. You could leave it as a fraction, but since this problem involves decimals, let's go ahead and just convert that to a decimal. So see, 80 divided by 61 is this complex number, 1.3115 if we round. Okay, now we can go ahead and plug that in over here to find b, which I'm out of space, so let's do it right here. So b is 80 divided by c, so 80 divided by 1.3115. Okay, I'm going to put this number in the denominator by hitting 1 over x and then multiply times 80. So we get 61, which I could have done algebraically as well. But anyway, so b is 61. Okay, so now we have the model then, which is y, or f of x, we'll just go with y, equals c, which is right here, 1 point. Actually, that does not make sense. Let's check that out. Oops, I see my error. You know how I realize that does not make sense is because the starting amount when x is 0 should be greater than 80, and I'm getting a small number, 1 point something. But I see my error here. I forgot to square that 80. So let's back up. Oops. And resolve for c there. Okay, so c is 80 squared divided by 61, which we will do on the calculator. So it's 80 squared over 61. So there's 80 squared divided by 61 is, there we go, that makes more sense, 104.918 roughly. 104.918. Okay, now let's solve for b. So then b would equal 80 divided by c, so 80 over that number. So let's put it in the denominator, multiply times 80, and we get 0.7625. Okay. Which you may remember is the same number we got when we did 61 divided by 80. It's the same reducing rate. Okay, so our model then is y equals c times b to the x. So 104, I'm going to cut it off early here for space sake. 104.9 times b, which is 0.7625 to the x. Okay, there's our model. Now, if this is an exponential function, then this